Now that we've looked at how to solve a system of equations with a matrix, now we can go back to talking about inconsistent or dependent systems of equations. So these are ones that are going to have multiple solutions or infinite solutions, or they're going to be ones that have no solutions. We can use Gaussian elimination on systems of three or more variables to determine how many solutions a system may have. In the cases of systems with no solutions, which are inconsistent, or infinite solutions, which is dependent, it is impossible to rewrite the augmenting matrix in its desired form, being that's going to be that form where we have. Oops, sorry, I'm trying to get my writing tool here. Being the form where you have, the one. And the zeros like this. Oops, I got an extra set of zeros there. So we're talking about this form like this, where we just have that row of zeros. Just put something random there. So we can't quite get to this form. What you're going to see is either we're going to have a row that doesn't make sense, or we're going to end up a row that's all zeros. We want to use Gaussian elimination to help us solve this particular equation. So let's make our matrix again. So our matrix here will be 1 minus 2 minus 1 minus 5, 2 minus 3 minus 1, 0, and 3 minus 4 minus 1, 1. As you see, this is going to be no solutions. We already see that at the top. We're just going to see what happens to let us know that we have no solutions. So the first thing I'm going to do is I am going to take the top row. I'm going to multiply it by -2 and then add it to the second row. Because if I do that, then we'll end up with a -2 plus a 2, and we can end up with a 0 here. So we're trying to still go at this the way we did before. So this row will be a -2, a +4, a +2, and a +10. So like I said, we're just going to keep the same row on top again. Really hard to draw straight lines with this pad. So -2 plus 2 is 0. 4 plus -3 is 1. 2 plus -1 is 1. And 10 plus 0 is 10. And then we're going to end up with 3 minus 4 minus 1, 1, because we didn't change that last row. So this time, we're going to take the top row and we're going to multiply it by -3, and we're going to add it to row 3. So now this top row is going to actually be a -3, 6, 3, and 15. So we'll put back the original row there. The second row, we already rewrote. So now our third row, got my augment. My third row is going to be -3 plus 3 is 0. 6 plus -4 is going to be 2. 3 plus -1 is going to be 2. And then we have a second. I think I got a typo here. I'm just trying to find it. No, I'm all right. We're going to have 15 plus 1 is going to be 16. I forgot this one should be no solutions. I thought I was looking for multiple solutions for a second. So from here, we could take this row, or we'll just do this. We can take, because we want a 0 here where this 2 is. So we're going to go -2, row 2, and add that to row 3. That means my second row is actually going to be a 0, a -2, a -2, and a -20. And this is where you're going to see if there's a problem. So 0 plus 0 stays 0. Negative 2 plus 2 is 0. Negative 2 plus 2 is 0. And negative 20 plus 16 is minus 4. So you notice right here, this row is telling me that I don't have an X, I don't have a Y, I don't have a Z. All I have is that I'm going to have 0 X plus 0 Y plus 0 Z is equal to minus 4, which is basically saying 0 is equal to minus 4. So we saw this in inconsistent systems before sometimes, is that when you end up with inequality that can't possibly happen, this is telling us that we have no solutions. What we have here is a system where you're going to have two of your lines or planes, or actually planes. We do three variable. So you have two planes that are going to be parallel to each other. So this would have been your row 1, and this would be your row, oh, sorry, this is your row 2, and this is your row 3. These ones are parallel to each other. Row 1 might intersect them at some point. And maybe it intersects like this, and it's going to go through. Let me draw that just a little better. It may intersect at some point. It's just that we see here is that we have a line here and a line here where maybe it intersects, but these two planes don't intersect. So there is not a single point or a single point where all three are going to cross at the same place. So like I said, what we have here is parallel planes. In this case, we're going to end up with infinite solutions. So when you end up with infinite solutions, like I said, because we're doing three variables, we can end up with having three planes. They're basically just going to intersect in this on a line or something like that. So if they all intersect, say, on the same line here, let's do one more. We'll put it up here. What we see is we have a line here that we got three planes are intersecting on that line. If you have a line, that's infinite solutions. You could also have like planes that are in the same spot that sit on top of each other, or three planes. It could be three planes sitting on top of each other, and you could just have one intersect both of them. Once again, you have a whole line here that they all intersect on. So once again, it's infinite solutions. There's a couple ways this can happen. So it could be like three planes sitting on each other, two planes are the same, one intersects them both. It could be they're all intersecting on a line. But what you're going to find here is you're going to get a system of infinite solutions. And we need a way to represent that. So let's make our matrix. So our matrix, it will end up being 1, -2, -1, 5. Then we'll have 2, -5, 3, 6. 1, -3, 4, and 1. Okay, so similar to what I did before, as we're going to use that top one because we got that one there to start doing some sort of elimination. So I don't always have to get rid of row 2 first. I could just go, well, let's just do -R1 plus R3. So this would just be -1, 2, 1, -5. And replacing the third row. Oops, let's get that a little closer. Like I said, this time I'm just attacking row 3 first. So -1 plus 1 is 0. 2 plus -3 is -1. 1 plus 4 is 5, and negative 5 plus 1 is negative 4. And then I can go negative 2 R1 plus R2 so that I can get rid of this 2 here. So I end up with 2 zeros under that 1. That means that R1 is now just going to be negative 2, 4 to negative 10. Oops, that's right. We're doing that row. So let me just write down my bottom one here that we already did. So we're replacing row 2. So negative 2 plus 2 is 0. 4 plus minus 5 is negative 1. Plus 3 is 5. Noticing something here, right? And then negative 10 plus 6 is going to be minus 4. We have the same line here and here. We got the basically negative y plus z equals negative 4 2 times. So let's say we're still trying to go, so we got a 1 here. We want it to be a positive 1, so we'll just change that to R2 is just going to be negative. I know we already see the problem. I'm just trying to follow this, pretending we didn't. Okay. So what I'm going to do is I'm going to take row 2 and add it to row 3 so I can get rid of that negative 1 there and have a 0 in that spot. And what that's going to leave me with is 1, negative 2, negative 1, 5, 0, 1, 5, negative 4, 0, and 1 plus negative 1 is 0. Oops, there's a typo I made here. I had these ones for backwards because I was changing everything from put a negative there. That should be positive 1, negative 5, positive 4. But anyways, negative 5 plus 5 is 0. 4 plus negative 4 is 0. So this row disappears. We get 0 equals 0, which is okay. We just can't have 0 equals 4 or 0 equals 5 or something like that. This tells me that I'm going to have two equations. Blue. So here we have x minus 2y minus z equals 5. And then we have y plus 5z equals minus 4. And then we have this equation where 0 equals 0. So that is 0z equals 0. So really what this is saying is that z could be anything. However, these two equations here are going to be dependent on that z, because once z changes here, it's going to change what if this z changes, it's going to change this y. If this z changes, it's going to change the y and it's going to change that. So we got x and y are dependent on z. So what happens in this case, make myself a little extra room here. If you need to, you might want to pause before I get rid of part of the screen. You keep writing down notes. I'm going to get rid of this part. So we said that we have a new system of equations, which is x minus negative 2y minus z equals 5. And then we have y plus 5z equals negative 4. And we said everything's dependent on z, right? So we want to solve for z. So the first thing we're going to do is going to take this equation. So we could take this one and we're going to have y plus 5z equals negative 4. Sorry, I have that wrong. Not solve for, I meant to say solve in terms of z. because we're dependent on the z, so z is my independent variable. Sorry about that, it wasn't a typo. Y plus 5z equals -4. So we're going to solve for y because z is going to be my independent variable. So y is going to be equal to second, I was just checking. I thought I had a typo. I don't have a typo. This is going to be, no, I do have a typo, just a moment. Yep, right here. So you probably caught that. I corrected it and then I didn't correct it again. Here, right, we changed R2, we said it was negative, so that was positive, -5, +4. That's where my typo was. What we have here is it's y minus 5z equals 4. Okay, yes, this is going to work now. So let me go back and fix here. The worst part about this is just making little silly mistakes. So y minus 5z equals 4. There we go. So y minus 5z equals 4. Solve for y. So what we're going to have here is y is going to be equal to 5z plus 4. So when you're over here and you're trying to figure out what your x, y, z is, what we have right now, I don't know what x is, but I know y can be replaced with 5z plus 4. And z is not going to be replaced with anything because everything is going to be dependent on z. So now I just need to figure out what x is. So x minus 2y minus z equals 5. We're going to do like that back substitution. So this is just x minus 2 times 5z plus 4 minus z equals 5. And we're going to solve for x. Because I have my z, I have my y, I just need my x. So x minus 10z minus 8 minus z equals 5. So this is going to be x minus 11z. If we add this 8 over here, this is going to equal 13. So this is going to be x is equal to 11z plus 13. So what you get here, because we have infinite solutions, is you're going to get something that's going to look like this for your system of equations. Like I said, we got rid of z here, so z could be anything we want it to be because 0z equals 0 means z can be anything. Which means that z is my independent variable that I can play around with. So whatever z is here, y is going to be dependent on that. And then whatever z is, y is dependent on that, which then here we're going to see x is going to be dependent as well. So everything is dependent on that z. So we make sure we write this all in terms of one variable. But like I said, just remember this is x, y, z. So instead of having a ordered pair of numbers, we have an ordered pair of equations. Not ordered pair, I'm sorry, ordered triplet of equations. Oops, sorry about the coughing fit. Gotta be a little careful because sometimes it's easy to make some mistakes doing this here. Okay, so what we're going to do here in a second is I'm going to give you two problems. One of them is going to be infinite solutions and one of them is going to be no solutions. So it's up to you to figure out which one's which. But let me get to those problems. Okay, like I said, so you're going to have worksheet 1. You have the problem. If it's no solutions, you're going to find no solutions to say it. If it's infinite solutions, then you're going to have an ordered triplet of equations, and they should all be in terms of z again, because most likely what you're going to eliminate is z. And the same thing here. This is worksheet 2. So this is either no solutions, or once again, it's going to be infinite solutions. So you get an ordered triplet of equations in terms of z. So like I said, one is no solutions, one is infinite solutions. So we got one of each here. Take a moment and work on both. Okay. So the matrix for your number one here is going to be 8, 5, 11, 30, then -1, -4, 2, 3, and then 2, oops, -1, 5, 12. So I'm going to do, to save kind of time here, I'm going to switch. We like to have a 1 up here, so I'm going to say we are going to switch R1 with R3, or sorry, R2. And not only is it going to be R2, I'm going to change it to a negative R2. So we're going to change this all from negative to positive. So we start out the way we'd like to with a +1 on top in the first little corner here. So we will have that -1 will become +1, that -4 will become +4, that 2 will become -2, and that 3 will become -3. Then our new row 2 is going to be the 8, 5, 11, 30, and then we'll have 2, -1, 5, and 12 again. So like I said, all I did is I just switched these two rows, and then I took this one and I multiply it by -1. So then, like I said, we just get 1, 4, -2, -3 instead. I just did two operations at once to save some space here. Okay, so we can do -8 R1 and add it to R2. Meaning this will be -8. This will be, sorry, -32. This will be, where was I? -8. This will be +16. And then this will be +24. So 1, 4, -2, -3. Now -8 plus 8 is 0. -32 plus 25 is -27. 16 plus 11 is going to be +27. And 24 plus 30 is going to be 54. And we have 2, -1, 5, and 12. And because we like to have a 1 here and then a 1 here, all I could do, I mean, I can easily do that just by going, okay, I'm going to take row 2 and divide it by -27. Like I said, we're going to go at this like we assume there's going to be a solution. We're not trying to prove there isn't one right away or if there's multiple solutions. We have 1, 4, -2, -3, and then we will have 0, +1, 24 divided by, 27 divided by -27 is -1, and 54 divided by -27 is going to be -2. All right. So let's try to get rid of this 2 here because we want a 0 there. So we're just going to say -2 R1 plus R3. Sorry, I'm trying to move something out of my screen. So we are going to have a -2, -8, 4, and 6. So we end up with the 1, 4, -2, -3, 0, 1, -1, -2. Then -2 plus 2 is 0. -8 plus -1 is -9. 4 plus 5 is +9. 6 plus 12 is 18. We're going to see here pretty quickly the situation we have here. We could just leave it like this because we just want to get rid of this -9. So we'll just go +9, R2 plus R3. So this will be 9, -9, and -18. So 1, 4, -2, -3. And then we'll have 0, 1, -1, -2. So 9 plus -9 is, or 0 plus 0 is 0. 9 plus -9 is 0. -9 plus 9 is 0. -18 plus 18 is also 0. So we got the situation once again where we got 0z equals 0. So z is going to be independent. This is telling me that I have y minus z equals -2. And this is telling me that I have x plus 4y minus 2z equals -6, -3. To make sure everything looks correct, yes. Make a little spot for me up here. So we just need to have our system here now. We're going to back substitute again. Z stays Z. Y is going to be y minus z equals -2, which means that y is going to be z minus 2. Then x is x plus 4y minus 2z equals -3, which is just going to be x plus 4. And then y is just going to be z minus 2 minus z equals -3. Then we have x plus 4z minus 8 minus 2z equals -3. So x plus 2z. If we add 8 to both sides, that's all going to equal 5. And so we have x is going to be 5 minus 2z. So my solution, like I said, it's an x, y, z, except we do not have numbers for that. It's going to be, sorry, x is going to be 5 minus 2z. Y is going to be z minus 2, and then z is going to stay z. So we have infinite solutions. We have infinite solutions, it's just that it's dependent on the set of equations. So it gives me a list of ordered pairs. Like if I know z is 0, well, then I know this is -2. Then I know that this is going to be a 5. Like I said, it tells me a set of ordered pairs. Or if z is 1, then I know that this is -1 and that this is 3. So it's going to give me a infinite set of ordered pairs. It's just that they're all connected on a line. Okay, so for this next one, well, we already got infinite solutions, so I think we know what's going to happen here. Said one is the one, one is the other. We have 2 minus 4, 1, 3, 1 minus 3, 1, 5, and then we have 3 minus 7, 2, and 12. So I'm just going to switch R1 with R2. So we have a 1 up here in the corner. So I'll just have 1 minus 3, 1, 5, and then we'll have 2 minus 4, 1, 3, and then we'll have 3 minus 7, 2, 12. So let's say we turn this 2 into a 0, so -2 R1 plus R2. That means that R1 is going to be a -2, +6, -2, -10. So we end up with 1, -3, 1, and 5. So -2 plus 2 is 0. 6 plus -4 is 2. -2 plus 1 is -1. And -10 plus 3 is -7. And we have 3, -7, 2, and 12 here. So I want to get rid of this 3. So if I do negative 3 R1 plus R3, well, that means this whole top equation is now negative 3, 9, negative 3, negative 15. Then put 0 to negative 1, negative 7. Then negative 3 plus 3 is 0. 9 plus negative 7 is 2. Negative 3 plus 2 is negative 1. And negative 15 plus 12 is negative 3. So I'll just do one more. Let's see, we want this 2 to go away. Technically we want this to turn to a 1, but we already see where this is going. So we'll just say, oh, okay, so if we do negative R2 plus R3, 1, negative 3, 1, and 5, 0, 2, negative 1, negative 7. So remember, R2 is all multiplied by negative, so this is actually negative 2, 1, and 7 right now. So 0 plus 0 is 0. Negative 2 plus 2 is 0. 1 plus negative 1 is 0. 7 plus negative 3 is negative 4. Or sorry, no, positive 4. Sorry, there was someone with a negative 4. It threw me off there for a second. So we see right here, this equation, once again, is telling me that 0 is equal to 4, which cannot happen. So we know we have no solution. We could have, like I said, it could be like 2 parallel planes. It could be 3 parallel planes. It's just somehow we have at least 2 planes that are not going to come together. Leaves us with no solution. Okay, another case where we can end up with infinite solutions is if we have less equations than we have variables. So if I had 4 variables but only 3 equations, one of my variables it's going to be the one that all the rest of them are going to be dependent on. So it's going to be like our infinite solutions case. We're going to make this easy. We're just going to do 3 variables but only 2 equations. We'll go a little bit further with the matrix E. We got a matrix E that looks like this: 1, 2, 3, 70, 0, 1, 2, 10. Where we got my 1 and my 0 and then my 1 here. So one of the things that you could do is like from here, we could go back and find our equations. So we have Z and then find Y and then find X. Another thing we could do here is we could actually use solving with the Gaussian elimination to sort of ease up this equation a little bit. Because if we wanted to do Gauss-Jordan elimination, we'd want this to be a 0. So what we're going to do is we are going to take negative R, go back, negative 2 R2 plus R1, because if I can make this a negative 2, I can turn that into a 0. This bottom equation is just going to be 0, negative 2, negative 4, negative 40. So what we're going to have is the bottom equation will stay the same. We're not changing that one. But we're going to take, like I said, this R2, this new one I made, and add it to R1. So 0 plus 1 stays 1. Negative 2 plus 2 turns into 0. Negative 4 plus 3 turns into negative 1. And negative 40 plus 20 turns into 3. Sorry, I don't know how I ended up with 40 there. I just noticed that. That should be at 20. For some reason, I thought I saw a 20 there. This is a 20. Negative 20. So we actually are left with a 50. I fix a couple things here. Let me go back and fix that one more time. It said negative 20 because I multiplied everything by -2 here. And then this stayed 10. And then this is 50. Okay, that makes a little more sense. Now what we see is I instantly have an equation where I'm not going to have a y here. This is just x minus z equals 50. And here I get y plus 2z equals 10. So easily I get my two equations because I could take this one and just rewrite it as x is just equal to z plus 50. And then this one is just y equals 10 minus 2z. So my solution, like I said, it's all going to be dependent on z. We said x is z plus 50. We said y is 10 minus 2z, and z is just z. We don't know what it's going to be. And once again, like I said, this is going to generate a line, once again, of equations. So it's a set that goes together, and it's an infinite set. It's just can't just be any combination of numbers. Like once again, if this was 1, this would be 8, and this would be 51. If this was 2, this would be 6, and this would be 52. Like I said, it'll generate a whole system or a whole line of equations for us. So try this one more time. You have three equations, but only, sorry, three variables, but only two equations. So you can use Gaussian elimination, or you can use Gauss-Jordan elimination. I'm going to use the Gauss-Jordan again, just because. And like I said, then we're going to end up with two equations, and then we just figure out what my whole system of, or my x, y, z in terms of z are going to be. All right, so our matrix would look like 1, 2, 3, 5, 0, 1, -5, 10. It's going to be very similar to the last one. If I want to turn this 2 into a 0, I just do -2 R2 plus R1, or row 2 plus row 1, meaning that this row is just -2, 10, -20. Maybe that's what I was looking at when I did the last one. So we're going to end up the bottom row is not changing at all. It's just our top one. So 0 plus 1 is 1. -2 plus 2 is 0. 10 plus 3 is 13. And -20 plus 5 is -15. Once again, we get two equations. We get x plus 13z equals -15. So we can just simply solve for x. And we get y minus 5z equals 10. So I can just simply solve for y. So x is just going to be minus 13z minus 15. And y is going to be 5z plus 10. -13z minus 15. 5z plus 10. And then z is my independent, so that's where it's going to go. I have to write solutions, not solution here, because we do have a set of solutions. Just make sure it all lines up. All right, and that is it for indeterminates, well, inconsistent systems or dependent systems. So this case here where we have three variables, two equations, so there's one variable we can't solve for, that is dependent. Everything's dependent on z. Infinite solutions, once again, we're writing them so everything's dependent on z. And then no solutions, as we end up finding an inconsistency like 0 equals anything but 0.